Shermin, can you Shermin has to rejoin. Can you let her know? And but Atika left also. Oh, they have to rejoin. Okay, never mind. We will continue. Okay, so so in vectors addition, we are looking at AD, vector AD plus vector DE plus vector EB. Okay, this will give us, you start from here. These are all continuous points. Or the same point. Okay, this is your ending point. Okay, this will give us A, B, vector AB. Okay. Okay, so this is known as the triangle law. So why is it called triangle law? Is because when we look at the vectors addition, point A to point D, and then point D to, let's say, point E. Okay, we are actually forming a triangle. If you want to walk from A to D, then D, you want to walk from A to D and then D to E, it's the same as you walk from A to E directly. Okay, that's what it means. That's why it's a triangle. Okay, so please note that the direction must be continuous. Okay, they must go up. It cannot be one across then one coming down. Okay, well, if they are in colliding directions, then it will be another technique. Okay, so you need to understand this because if you're asked to draw vectors, okay, you need to know how it works, how the vectors work. Okay, so just remember that vectors are just lines that you can actually transfer around. Okay, they are not rigid lines. That means if it's there, it's there. You cannot, it's not that, it doesn't work that way. Okay, you can actually transfer that vector to another location to make them connect. Okay, so what happens? What happens? What happens if two vectors are in opposite direction or heading or going towards each other? Okay, so not every time when you will see vectors in going in a continuous direction. Okay, sometimes they may be going away, sometimes it may be going towards. Okay, so example 1, they are going in opposite direction. Yeah, I'm gonna just copy the whole thing. Caitlin, you just leave a space because this is what I have written before you came in. Okay, later I will send the document to you and you can look at it. Okay, in opposite directions. Let's say we have this way and this way. This way. Okay, so just remember that we can shift vectors around. Okay, we can shift vectors around. Okay, so what we can do is you can either move this vector to this point here, or you can move this vector upwards to this point here. Okay, so whatever it is, you will notice that this vector point A is our start point. Okay, so if you want to move AC also can, if you want to move BC also can, it doesn't matter. Okay, let's say if you want to move AC, then it would be 4, 5, 6. You'll be here. No. Okay, this is our moving up. This is like your A, C here. Okay, or if you want to move AB, it will be, you will have to, because your starting point is at A, you're starting at A, when you move along AC, you stop here. So you have to continue in this direction to make it work. So if you want to move AB out, then it would be like this. Okay, and you notice that we actually form a parallelogram. Okay, so whether you walk this way or you walk this way, you walk this way or you walk this way, you notice that you end up at this is a common point here. This is your ending. Okay, so our final vector would be this way. Okay, this is our final vector. So in this case, if we are looking at, okay, if you are looking at AB, if you are walking from A to B, then you have to continue from A to C. Okay, you will end up with A, C. Okay, note that this is a shifted vector. Okay, we have shifted away from its original location to another place that you can continue the pathway. Okay, or you could see it as looking at AC, you start from A, you walk along AC, okay, and then you continue with this vector AB. Right here, you will get vector AB. Okay, no. Yep. Okay, let's call this a new number, day. So here would be day. This is day. So this is what we call a parallelogram law. Okay, because what we are doing is we are actually drawing a parallelogram to add the vectors. Okay, also recall that a vector we can indicate a vector using a letter. Okay, example, let's say this vector is called vector A. Okay, so that means this line, okay, this line here with this direction is known as vector A. You all remember this, right? I talked about this the last lesson. By the way, those who have handed in your homework, it's ready for collection. You can pick it up from the same file. And then the answers or the solutions, I've dropped it in as well, so you can have a look. If you're not sure, then just ask. Okay. Pause here for a while for you to write. Those are done. You can look at try it. Try it on page 168. Anjali, you're still writing, is it? Okay.
Okay, done.
You're done.
Yeah.
Anyone still writing the notes? I think are you very cold? Okay, so I've taken a picture of the book of the question. And this is try 8. Okay, so here they want you to draw a diagram to find each of the following vector sums and express each sum as a column vector. Okay, so very quickly, because the keyword here is they want a column vector, let's just identify the column vectors first. Okay, if you have vector P, this is, you're going 1, 2, 3 downward, so it's -3 on the x-axis, and sorry, this is y, so this is -3 here. And then 1, 2, 3 across, this is +3, this is -3, so this is 3, this is 3 minus 3. Okay, so as you can see, I have written outside the bracket is what? Okay, outside the bracket, it's P, nice, P with a little tail at the bottom. Okay, this is to indicate a vector. So for small letters, on print, we use bold, but when you're writing, you can't bold the letter. Okay, so what we do is we use lowercase, small letters, and then we put a little wiggly line below it to indicate a vector. Okay, to differentiate between algebra and vector. Okay, so just to quickly, if you have done it or if you have looked at the column vectors for each of them, Q would be, you're going up 1 unit. So this is Y value. And then you are going to the left by -3. So this is -3, 1. I'm just going to erase all of them because we need to draw later.
Miss Ting, is it a must to put the arrow?
What arrow?
Look, you know when you draw, then there's not got arrow. Like down arrow, to the right arrow. You get it?
Where?
Like, you know when you drew the P, then you draw like -3, then there's an arrow. Okay,
-3? Don't have what?
Never mind, never mind.
Okay.
Are you talking about the wiggly line?
No, like, okay, wait, let me try to flip this thing. Hey, can you see? Can you see? It's like the arrow.
Oh,
I can like this
okay. So
one.
what I have done just now is it like the ones that are
Yeah.
erased? Hold on, I erased something. This is okay. This thing here that I drew on my diagram, the graph on the vector, no need to draw. I'm just counting myself, but I write it out so that you can see.
Oh, okay.
Yeah.
Okay.
Okay. What was it doing? Okay, then right. Okay, so I'm erasing all these markings on the graph because I need you to draw later. Okay, this is just trying to show you what I'm doing to get the column vectors. So for R, okay, we move to the right by 1 unit. So this is x-axis is -1. Okay, you are going downwards along the y by -3. Okay, so this is -1, -3. Erase this. Okay, so for part A, you want vector P plus vector Q. Now, P plus vector Q is, look at these two lines. Okay, so you can start with vector P, you can start with vector P, then add vector Q, or you can start with vector Q, then add vector P. Doesn't matter. Okay, so later on we will see that whichever direction, whichever pathway it works, okay, it will still give you the same destination. Okay, whether you start from P, then you use Q, or you use Q, then you use P, it will still give you the same point. Okay, I'm going to use Q first, or you can use P. Okay, let's use P. So P, we are here. Wait. Okay, so for P, we are here. This is our start. Okay, so we walk along P, and then we stop here. Okay, this is like our first stop. And then you go hiking or you go walking, sometimes you stop along the way, right? This is where you stop. Okay, and then you decide to take another path. The other path is vector Q. So vector Q has this direction. Okay, but it's out there. So how do we continue from where we stop? We translate this downwards and make it continuous. So vector Q, you are walking from here, you are walking 1, 2, 3 units to the left. So from here, we are walking 1, 2, 3 units to the left, and then 1 unit upwards. So 1 unit upwards. Okay, so we are drawing this line here as vector Q. Okay, let me use a different color for the indication. 1, 2, 3, 1 unit here. Okay, so we end here. So if we start from here and we took this path and we ended here, it is the same as we actually start from here and then walk straight down and you get to your ending point. Okay, the shortcut. So this is actually the shortcut. Get it? Okay, this is vector addition. Okay, you are looking for the shortest path. Actually, you walk along a lot. You walk a lot of routes. Okay, but actually the shortest path is just a straight line connecting your starting point and the ending point. Okay, that is what we are looking at when we add vectors. Okay, so this shortcut, what is the column vector here? You do not move anywhere out of your x-axis. If you notice, okay, you did not step out of the x-axis. You are just going downwards by 2 units. So P plus vector Q, we would end up with a column vector of 0, -2. Okay, from where you started, you just move 2 units down, you'll get to your ending point. Okay, using the 2 vectors, the direction from the 2 vectors. Okay, so let's check. Do we get the same answer as we use column vector addition? Okay, we check. Is -3 -3. They add the column vector -3, 1. Okay, this 3 plus -3, I get 0. 3 -3 plus 1, I get -2. Okay, it is the same as what we have drawn. Okay. Okay, so part B, you are looking at R plus P. So vector R plus vector P. Okay, so vector R is here. You need to add with vector P. So vector P, let's use this R plus a vector P here. Okay, we're going to continue. So red, we will start here. Okay, we pause at this point. And then we continue with a vector P. Vector P are going downwards by 3 units. So I'm moving downwards by 3 units. And then across by 3 units. So you end up here. Well, actually the correct way, right, is to take the ruler and then you shift the whole vector down, okay, with the same distance. Okay, but now the shortcut is actually to count. Okay, if you're not sure, you look at your book. So this is 1 unit, 2 units, 3 units downwards here. And then from here, you move 1 unit, 2 unit, 3 units to the right. 1, 2, 3 to the right. Okay, that's where you end. So this is the same as from start, you draw a straight line all the way down to the end. Purple. Okay, this is the shortcut, which is actually our final vector. Okay, so let's count this. This one from the start, you move, wrong. Oh, I erased it. Okay, so from the start, to get from here to here, you actually have to move out by 2 units. Okay, so this is 2 units. And then from here, you move up by 2 units, you are here, then you move 1 unit, 2, 3, 4, 5, 6 to get down. Okay, so it's -6 on the y-axis. Okay, so we check again using the column vectors that we know. So we have vector r plus vector p. Vector r is -1, -3. And then you add with p is 3 minus 3. You will get, so 1, -1 plus 3, you get 2, which is what we have. Okay, and then -3 plus -3, we get -6. Okay, which is actually the answer. Okay. So this is column vector, vector addition. So usually when we look at not more complicated diagrams later on, okay, you will notice that you will have to find equal vectors to kind of shift your path. Okay, I will give you examples later on. Okay, so does it matter if, let's say, I don't want to start with R? I don't want to start with R for part B. I don't want to start with R, but I want to start with Q, then I add R. It's the same. Okay, so if I start with Q, then I add R. I'm just going to erase. I don't feel like erasing everything. Okay, I'm just going to use a different color. Okay, so if I start with P, and then I want to add R. Now R, we are walking downwards by 3 units. So we have 1, 2, 3 units. And then from here, we walk to the left by 1 unit. So we end up here. Okay. This is vector R. Okay, so if you can see, this is going to be very messy. There is a vector here. Okay, this is for part B. Okay, now if you count this, 1, 2, 1, 2, 3, 4, 5, 6, it is the same column vector. So regardless of which vector you use to start it, you will still end up with the same answer. Okay, because this works because of the parallelogram rule. Okay, so parallelogram, you know, two pairs of parallel sides. So no matter where you translate the diagonals, so you will end up the same. Okay. So okay, I move on here. Okay, next one. Okay, so vector subtraction. Actually, we don't subtract vectors. Okay, what we do is instead we add negative vectors. Okay, so example, if we have vector A minus vector B, okay, this is the same as vector A plus negative of vector B. Okay, this one quite straightforward, right? Because if you think about algebra, it's gonna rain very heavily soon, okay? Yeah, Jelly, you never sing and also raining.
We can rain, right? Because I sing.
You sing and we can. Wow.
Yeah, I did.
Thunderstorm.
That's why you right. Okay, later I try.
No need. It's going to rain soon, I think.
My house here, the clouds are dark.
Mine also quite dark. It's quite windy.
Because maybe I was jamming to music just now, so maybe that's why.
Oh.
Okay, got plane. Wait.
Oh no, where did Lisa disappear to? Okay, never mind. So if you remember your algebra, if I have A minus B. Hello, good morning, Rubina. Are you here? Where did she disappear to? Okay. Okay, so if you remember your algebra, if you have A minus B, it's the same as A plus negative B. Okay? So for vectors, it's the same. Okay, remember vectors, we don't subtract, we add. Okay, this one, we add. So what does the negative mean here? What does this negative mean? Okay, this negative we call if you have a vector and it's negative in front. Okay, so the negative means opposite direction. Okay. All right, but okay, this is a bit of confusing, but in column vector form, okay, my handwriting so bad. Vector form. Okay, subtraction, we will just subtract normally. We will subtract as per normal. Okay, meaning if I have vectors, let's use the numbers above. Okay, 3 minus 3, and I minus this vector, okay, -1, -3. Okay, we can just perform it. You know, like your matrices, right? When you subtract matrices, you just subtract the numbers accordingly. So this is the same as 3 minus -1 and -3 minus -3. Okay, which will give me 4 and 0. Okay. Okay, so on the diagram, so how does this look like on diagrams? Okay, I give you an example here. Okay, I have vector V, and then I have vector U. Okay, what we want you to do, vector V, vector U minus vector V. Okay, we want this. Okay, so you have a subtraction. Now, if you look at this, vector U minus vector V is vector U plus negative or vector V. Okay, because we add, because we always look at vector addition because we are adding our pathways. Okay, we always add on. Okay, we don't remove the pathway. Okay, So here, what we are doing is we are adding a negative vector v. Okay, so if you look at your diagram, vector v is here. It is going upwards. So what does a negative vector v look like? Negative vector v, let's use purple. Negative vector v will have the same length, but instead it will be going downwards. This is negative vector v. Okay, so if we are using u, vector u plus a negative vector v, okay, it is the same as you are walking down this way. Okay, you're walking down this way, and then you're going this way. Okay, you're doing this way and this way. So what do you end up? You actually end up with this answer. Actually, no, they want. Yeah, it's the same. Okay, so you will end up with vector u minus vector v. This is the answer. Okay, I'm actually going downwards. I'm going downwards, then I'm going across. Okay, now what if I want to follow this instructions here? You start with vector u, and then you add a negative vector v. It's the same. Okay, if I start with u, I am here. Okay, I start from here, and I stop at here. Then I continue with vector v downwards, negative downwards. So here is this length. So what do I get? I get from here, this is my start. This is my end. Okay, this is the pause point, the checkpoint. Okay, so you end up with this. Okay, the lazy way, eventually you will notice that everybody starts writing like that. Okay, that's fine as well, because of to save time. If you wiggle, it takes a bit of time. Okay, so eventually you will notice that a lot of people just write the line underneath. Okay, so is this vector and this vector the same? Are they equal? Are they equal? Is this and this the same? They look somewhat the same, right? Because they have the same expression. Okay, how do we know that they are the same? We check the column vectors. Okay, this is actually the same as this. Okay, they're actually parallel lines and they are equal in length. Okay, they have the way. So equal vectors, they have same direction. They must have the same length or magnitude. Okay, so they are pointing in the same direction, this way, this way. Okay, if you measure, they have the same length as well. Okay, by counting the steps horizontally and vertically, they have the same steps. Okay, so they are actually equal. All right. Now, I want you to look at example 13 on page 175. I know it's an example. My iPad here. Hello. Okay. Okay, I know it's an example. The answer has there's solution given to you, but actually the solution is on the other side. So I don't look at it. So let's look at this. Why I focus so much on this? Why am I looking at example 13? You just read quickly. It's because it's a hexagon. C, D, F. This is vector R. This is vector Q. This is vector P. Okay. So for a hexagon, it's very special. You have done one question in the homework question on exercise 6.1. Okay, so hexagon, they always like to use hexagon for vectors question or some other things. When it has a regular, of all the regular polygons, they always choose hexagon because of its special features. Okay, hexagon, it comprises of 6 sides. Okay, so if you divide equally, you will get 6 triangles. Now, these 6 triangles are not any other triangles. These are equilateral triangles. Do not spell equi. Okay, they are equilateral triangles. Okay, so what's so unique about equilateral triangles? All sides are of same length. Okay, all the sides are of the same length, but you need to take note here. Although everything is of the same length, some of the directions matters when it comes to vectors. Okay, so let's indicate the parts that have the same vectors. They're of the same vectors. Okay, if I'm using, let's say, purple for P. Okay, so those that have the same vector as P, which is AB, vector AB. Okay, the center is O. Okay, those that are of same vector as P, you have FO, you have OC, and also ED as well. Okay, let's enlarge this a bit more. Okay, so these are the parts with the same vector. Now, from F, this vector P here, F is only from F to O. And then from O to C is another vector of the same, is not another same vector P. Okay, these are the things you need to take note. Actually, I'm quite surprised that those who submitted homework, you know what to do. Okay, because a lot of people in the past, when they did vectors and they look at hexagons, they always messed up because they say, oh, because they're all the same sides, all same length, right? They all have the same vectors. Okay, but it's no. Okay, so remember, vectors must be in the same direction. Okay, let's use green for R. Okay, so if we are looking at vector R, use a darker one. Okay, vector R is going downwards. Okay, so vector R, what are the ones that are similar? This one, this is vector R, this is vector R, and this is vector R. Okay, let me draw a bit bigger. And so if we use red for vector Q, okay, vector Q is going upwards. So those that are corresponding to, that equal to vector Q would be this OE, okay, in the same direction, BO, and AF. Okay, it's very messy here. Okay, but I hope the color coding will help you to orientate yourself a bit on the hexagon. Okay, so identify part A, part 1. identify the vectors which are equal to Q. So Q would be, other than AB, we have, you're looking at Q, right? So all the red ones. So other than CD, okay, I'm just going to make a note here. This is vector CD. We have vector AF. Okay, this is also equal to vector OE. This is also equal to vector BO. Okay, they are equal vectors. All right, so please remember vectors, when you name them, the order is important. So order is important. How you name vectors is important. Okay, so the next part, for part 2, we have vector R. Now vector R, if you look at your diagram, is actually EF. Okay, so EF here, those are in green. The vectors which are in green, we have DO, OA, and CB. Okay, now does it matter if in this case when he asks this kind of questions, right, identify the equal vectors, does it matter which vector, which set of vectors comes in first? No. Okay, as long as you can tell me all this is, you are correct already. Okay, it doesn't matter. So some of you may put CB first, then DO, then OA. Okay, then some people may put in other order. Okay, that is fine. Okay. Okay, so we have next part, B part 1, okay, P plus Q plus R. Now, although it's not exempted, it's not tested for exams. This one, when you're writing vectors, a lot of people eventually, they tend to miss out the lines below. Okay, so please remember that when it's a vector, you have to indicate clearly that it's a vector that you're talking about. Okay, if you don't put in the lines, it becomes a normal unknown PQR. Anjali, you're very strong. Your video is on the other side. You are like 90 degrees.
Yeah, because I'm charging my phone. It's gonna die.
Oh, okay.
Yeah.
Okay, so you have vector P plus Q plus R. So how do we do this? So if you look at your diagram, okay, you can pick any one. So since they want P plus Q plus R, so P plus Q plus R. So what do you notice? I just drew a triangle and I end back at the same point. Okay, now what if I want to try another set of vectors? Let's say I want to use FO. FO also has PQR. F is P, FO is P. Then I want Q. I have to walk up, continue going up. And then at R, I just have a vector R as well. I'm continuing downwards. I end back at the same point. Okay, so here you can say that this is actually vector AA. Okay, some of you may say this is vector FF. Or some of you, are there any other options available? OO as well. Okay. Okay, so what do this mean? This is a zero vector. A zero vector means you start and end at the same point. Okay, you will start and end at the same point. So the magnitude equals to 0, direction, and it has no direction. Okay, so it's like, imagine you step out of your classroom, then you turn right to the lift area, right? Then you take the staircase down to the 5th floor. You walk along all the whole corridor of level 5, and then you go up the other end of the staircase, and then you walk down your corridor, and then you come back to your classroom. Okay, that's a 0 vector. Okay, that's what it means. Okay, you walk one round and you end back at the same place, that's 0 vector. You don't want to go to level 5 also can. You want to go level 3, level 2, level 1. You want to make many loops also can. But as long as you end up, you come back and you end at the same point, the same classroom, it's a 0 vector. Okay, it's as if you did not move at all. Okay, yeah. Anjali, why you laugh? Yeah. So you can be like Miss Chan, if you go out of the office, but you make like you walk. She always walk right everywhere. She walk. When she ends at the office, it means her vector is actually a 0 vector. Okay. Part 2, you have Q minus P. Q minus P, again, this we don't subtract vectors, we add. So this is Q plus negative P. Okay, so if we look at our diagram, you just pick a vector Q. If you want, you can pick the one that we are talking about. Is indicated on the diagram. So a vector Q, and you want an opposite P. So a negative P. A negative P would be this direction. Okay, so it so happened that at this point, CD, there is a negative P, which is here. Okay, so you start from C to D and then from D to E. So it's the same as you walk from C to E. Okay, so the resultant vector here would be C, E. Okay, so is this the only answer? No, I can have many other Qs. I can have this, then I do this. Okay, I can have BF as my answer. It depends on which vector Q you are picking. Okay, it depends on the vector Q that you are looking at. Okay, or if you think about it, CE, which other vectors has the same direction as CE? We can do this. This is equal to BF. So this is actually the same as BF as well. They are equal vectors. Okay, but in actual question, it will not just be free for all to choose from. Okay, usually they will give you the notation that they want you. They will give you the starting point. Okay, so for example, they may say, oh, vector CD. Okay, they may say express in terms of P and Q, vector CD plus vector DE. It's more of that cases. Okay, but for this practice, I want you to understand how addition subtraction works. Okay, and then for last part, P minus Q minus R. Okay, so this is the same as vector Q plus negative P, then plus a negative R. Okay, so if you realize this portion came from part 2. Okay, so now you just need to add a negative R. So where we were stopping just now, okay, we have vector this plus this. So we know that from here, we walk to here. Okay, now you want a negative R. So it doesn't work quite well in this case because you are restricted by what you have in the hexagon. So you cannot add a negative, or you cannot just shift the vector out. Okay, so here we are going to look at this instead. BO, okay, O to F, and then negative R is this direction. Okay, so if you notice, B to O plus a negative P plus a negative R, it gets me from here. So it's the same as all the way up. So it's the same as EB. Oh, sorry, B, E, vector B to vector E. Okay, now this case, this example, this part here is unique because there is only one line in the hexagon that satisfies this root. Okay, so I explained just now, if you cannot start from D, you cannot start from C to D, and then from D to E, because there's no way to continue from E using a negative R. Okay, so for diagrams like hexagons, if you are given a diagram, you are restricted to the roots or the lines that you have on the diagram for your vectors. Clear? That means you only have these routes to take. You cannot create your own road to move. Okay?
Teacher, wait. Can you go
Yeah,
back down?
yeah. Can.
Thank you.
I'm just going to finish off with scalar multiple, and then we are done for today. Tomorrow, you will do, okay, then you will read through the textbook again and then go through some questions for tomorrow. What did I put for tomorrow? Okay. Then. All right. Last part. Just finish it quickly. Scalar multiple. Okay, a scalar multiple extends or shrinks a vector by an amount. Okay, so if we have this as vector A vector 2A will be twice the length. Will it be in the same direction? Yes, because you are still talking about the same vector. You're just 2A means you just times 2 of vector A. If I have half A, means you cut the vector by half, wrong direction. So here, half the length of vector A. Okay, still same direction. Okay, this one, same direction. Can we have a different direction with different length? Yes. Okay. So if we have this, and I put like that, this is minus 2a. Okay, so a negative scalar changes the direction. And length. Okay, we know how the numbers will affect the length. If you put a negative sign, it just changes the direction. That's all. Okay, everything else applies. So for column vector, it works as per normal, like your column matrix. Okay, there's something else I need to talk about here. Am I moving too fast? Don't need time to copy. Okay. Parallel vectors. Okay, so parallel vectors are important because the vectors are parallel. When the vectors are parallel, vectors have the same direction, okay, but they are different in length. Okay, so if we say that this is vector P and there's a vector Q, okay, and we say that if we say that vector P is parallel to vector Q, okay, what it means is that P is a scalar multiple of vector Q. Okay, so then it is your job to actually go and figure out what is this scalar multiple. Okay, usually it is, sometimes it may be a whole number, sometimes it may be a fraction. Okay, so do I have an example for you? Okay, example before we end off. Okay, I'm using exercise 6.2, question 11. Okay, vector P is 8, negative 10, and Q equals to n 15. Okay, you are given that P and Q are parallel. Okay, find value of n. Okay, so we know that they are parallel. Shade this nicer a bit. Parallel. So what happens if they are parallel? We know that P is a scalar multiple of Q. Now, can we change it the other way around? You can also put the other way around. Q is a scalar multiple of P. Okay, it doesn't matter because they are parallel. It works the same way. It's just that your answers will be different. Okay, the K value will be different. Okay, so I'm going to use P is a scalar multiple of Q. So let's substitute the column vectors in. So what we have here is Kn and 15K equals to 8 and negative 10. Okay, so when you compare, which one can we compare first? Okay, we can compare the one at the bottom because it will tell us what is the K value. Okay, negative 10 equals to 15K. K will be negative 10 over 15, which would be minus 2/3. Okay, therefore, using the top, now we compare the top value, Kn equals to 8. We have 2/3 of n equals to 8. 2n is 24. N would be 12. Okay, that's what it means by parallel. Okay, so that's all for today. The homework questions you can do tomorrow, which is Tuesday. Apart from the other thing that the other thing that I asked you to do for tomorrow is your practice paper. I asked you to finish up paper 1 of April's paper. The last time we did, we only asked you to do half. I only asked you to do half. Okay, exercise 6.2, question 9, 10, 13, and 14. Okay, this is one thing. Second thing is the second half of April paper 1. I think the answers have already been uploaded on SLS. So if you have seen, if you notice the answers are there, just check it when you are done with the papers. Okay. Paper 2, I will send you the link. I will send you the soft copy if you need. Because I know some of you, like quite a number of you, did not take the papers. You think we bring for fun. Okay. Okay. Thank you. Please do your homework and also finish up the April paper. If you are missing the March paper and you want me to send you the March paper soft copy, please let me know. Okay, type in the group chat to alert me that I can send it to you. Okay. Tomorrow, yeah, you can use tomorrow's lesson to finish up the homework. Yes, I'm not going to rush through vectors. I'm just going to take it slow and easy because it's not that important. Like, not that important because it's not in O levels anymore for this year. This year only, this year, you're lucky, this year only, okay? But you all still need to know. All right? Okay, so that's it. Bye. Thank you, everybody, for coming.
Bye.